I'm just waiting right now. Say hi, Angel.
All right.
It's the glass breaker.
This is the glass breaking class.
Yeah.
So the ground breaking or glass breaking.
Yeah. It's okay. Glass can be replaced.
We only have 2 cups left.
Is the sound of the air conditioning, is that too distracting for you guys? Okay, good, because it's freaking hot in here. Good. Okay, it's 4 o'clock, so let's go ahead and get started today. All right, so good afternoon, everybody. How's everybody doing today? It's Thursday of week 14. So we're quickly winding down the semester. So after this week, we only have 2 more weeks to go, right? Yeah, it's going by fast. This is the part of the semester where things start to ramp up, where everyone gets really busy and everything is due. So it's definitely goes too fast. But I think this is the time when I think everyone wants a bit more time this semester. Okay, so the plan for today is I have 2 handouts that I want to go over today. So hopefully those will help some of you guys out for your projects. So we're continuing the theme of learning kind of miscellaneous, not miscellaneous, but I mean they're important Ansys skills, but maybe not everyone would have to use them. But what I'm hoping is that these handouts will be useful to some of you. Okay. So today I plan to go over the handout on creating kind of phantom surfaces within your Ansys model, because a lot of you guys have curved surfaces, or you have kind of interesting ways to apply forces on your system, and you need kind of an extra surface to do that. So we're going to go over that, and then after that we're going to go over how to input anisotropic materials into Ansys. Okay. All right. So the question. So do you give feedback on the project progress report? So yes, I'm going to give you guys feedback on the progress reports. So remember that's due today. But I have an exam I need to grade tomorrow, so I'll probably give you guys feedback on Monday. But yes, I do plan to give you guys feedback on your progress reports. So please make sure to get those in. Even though it might have said it was due, I think at 4 p.m. today, please just try to get it in sometime before midnight tonight, and I'll give you guys feedback on Monday. Okay. Okay. Are there any questions before we get started today? Either based on what we've covered so far, or just okay, good. It's already due by 11:59. That's good. Either based on what we've covered so far, or just any other questions I can answer. Okay, so let's go ahead and get started. So let me share my screen. I close Reddit first. Okay. So the first thing we're going to do today is we're going to learn how to import or basically implement a what's called like an arbitrary surface for force calculation. Okay. So the handout for this is posted on Titanium. Okay, so it's a short handout. It's only 6 pages. And basically what I'm going to walk you through is basically how to create kind of an extra surface on this model in order for us to apply basically boundary conditions. Okay. So what I have for you right now is I've created a cylinder here on in Design Modeler. So it's a very basic cylinder. So if we say that, maybe we want the cylinder to represent something like a rolling pin, or maybe part of a wheel. And what we want to model is, like, say we want to model the contact force between the rolling pin and the ground. Okay. So say, you know, the ground is kind of resting underneath the curved part of the rolling pin down here. Right. So in order to apply that force, we know that the rolling pin is only going to contact the ground for a small kind of portion of its area. It's not going to contact the whole thing. But if you try to select the face, you know, if you go to like kind of face select mode here in the top of Design Modeler, you can see that the only thing that you can select is the entire lateral surface of the cylinder, which is not what we want, right? So all we want is basically we just want a small slice. Okay? And so what we're going to do is we're going to learn how to use the projection tool within Design Modeler in order to input basically new surfaces for you to apply forces. Okay? So for those of you who are doing final projects that involve a car of some kind and you want to model kind of the contact force between the car and the ground, this could be something that might be interesting to you. Or if you are doing something like I know a few of you guys are doing things like skateboards and surfboards, and you want to model kind of the force of someone standing on top of it, what you need to do is what you can do is you can kind of project kind of a foot-shaped projection onto your skateboard so that you can apply the force of a person pretty much directly on where they would be standing. So there's kind of a lot of applications for this. So we saw a little bit of this already in Ansys Activity 3, because if you remember in Ansys Activity 3, we did the Ansys analysis of a signpost. So in order to apply kind of our wind force on the left-hand side of the signpost, we had that kind of phantom surface there that kind of bonded to the structure to make sure that we can apply that wind force on that small thin part. Okay? So all of this, you know, all of those things would be great for this. All right, and like I mentioned, the main tool that we're going to use here is called projection. So just to kind of give a preview, so the projection tool is here under tools. If you go under tools on your design modeler and you click projection. Okay? But before we get there, we need to kind of define some things to help us out. Okay. And along the way, we'll kind of learn some additional kind of basic design modeler skills that you might find useful for other applications as well. Okay, so the first thing that we need to do is we need to create a new plane, okay? Because right now the only planes that we have available to us are these these three planes. We have the basic XY plane, we have the ZX plane, and we have the YZ plane. Okay, so these are fine because they define kind of the origin planes of our system. But in order for us to project a drawing, which is essentially what we're going to do, we're going to project a sketch onto our solid. We need to offset the plane so that kind of our projection kind of starts from somewhere else. Okay, so we're going to need the first thing we're going to learn is how to create a new plane. Okay? So the way we're going to do that is we're going to go up to the create part. Okay, so if we go up to the top of the menu here and we click create, and you can see here we can create a lot of different things. So you can see that there's you have kind of basic SolidWorks. You know, actions here too. So you can extrude sketches, you can revolve them, you can create like a chamfer or a blend. A blend is the same thing as a what's called a fillet. Okay. But the thing that we're going to create here is a new plane. So let's go ahead and click that. Okay. So you can see we've created a new plane called plane 4. Right. And the way that we're going to define this plane is we're going to use the details that are in the bottom left. So there's different ways that you can create a plane. Okay. So one common way that you can create a plane is you can create a plane based off of face. Okay. So what you can do is you can say that, you know, let me select this face right here. So click base face here and make sure that we're on face select, and we can select that one. And then what you can see here is that we're creating a plane that's centered on this face right here. Okay. So that might be useful. Say you want to sketch kind of a new feature that's on here. And the the XYZ planes are kind of on the back there, right? So if you want to create a new feature that's on this plane, you can create a plane type, and you can say from face right here, okay? And then select this, right? So that's one application for this, but we're not going to use it for that. The way that we're going to do this is we're going to select kind of a base plane as one of the XYZ planes. So let's change the type of plane to be from plane. So what that means is that we're creating a new plane from another plane. And so let's select the, let's select the XY plane. Okay. So let's select the XY plane because I want the plane that's basically parallel to the screen right now. So you can see I have the X direction going from the X coordinate going into X with the red arrow and the Y coordinate going with the green arrow. So that's kind of, lateral to our surface here. So we can see that our base point here is the XY. Okay. So let's go ahead and apply. So that's good. Okay. And then what we're going to do is we're going to change this transform type. Okay. Because what we can do from here is that now that we've selected a base plane, we can offset it in any direction that we want. Okay. So in this case, you can see all the different options here. So what we're going to do is we're going to offset it in terms of Z. Okay. So that'll basically allow us to move our sketch plane within the Z direction, or within the direction of this blue arrow here. And let's offset it by a certain amount. So for this case, the amount that you want to offset it is you want to offset it basically so that it's basically just off your surface here. Okay. So in this particular case, I think the radius that I put in here was 5. So let me try 5 and we see this. Okay. Yep. So since the radius that I picked, or the diameter for the cylinder that I picked was 10 centimeters, you can see that this offset plane that I'm creating is offset exactly by 5 centimeters right here. So you can see it's basically just barely touching that. And that's good. And that's basically exactly what we want. Okay. So then once we've done that, once we've selected the base plane and we've selected the offset, we can go ahead and click generate. Okay. And you can see now that we've created this this plane, which is right off the cylinder's edge right there. So then now that we've defined this plane, we can sketch in this plane now and define kind of the shape that we want to basically export or project onto our surface. All right, are there any questions on how to create new planes within Design Modeler? Okay. So then let's go ahead and start sketching. So the next step here is we need to sketch basically the shapes that we want to project. Because in this plane, what we can do is we can draw shapes. So let's go ahead and center it on the Z-axis so that we can see what's going on here. Okay. Let's zoom out a bit, just so we can see. Okay. So then once we've created our plane, let's go ahead and left-click it. So we've left-clicked our new plane forward. And of course, you can give this a new name to help you be more descriptive. So let's call this projecting plane. Right, so then once we do that, we can go into sketch and we can draw the shapes of the things that we want to project. Okay? So in this case, let's draw a rectangle. Okay? And let's draw a rectangle just like that. Right? So we can give this some dimensions. So we can say that this rectangle, I'm just going to give it arbitrary directions. So let's say it's going to be 15 centimeters across. Okay. And then the height of this rectangle, let's give it 5. And just to make sure that it's centered on our axis, let's change this guy to 2.5. Okay. And then let's have a horizontal offset here of 10. So that was completely arbitrary. So for your case, you would know kind of where you want to place this projection more specifically. But for this case, just for demonstration purposes, I just made just kind of a random rectangle there. So then once you have the sketch here, what you can imagine is if you kind of turn the geometry this way, what we're going to do is we're going to take this sketch and we're going to project it onto this cylinder to create kind of a new surface. Okay. So then once we've drawn our sketch and we're kind of happy with what we're going to project, we're good to go here. And so the next thing that we're going to do is a little bit non-intuitive. So we need to actually extrude this sketch, but we need to extrude it as what's called a frozen surface. And so what frozen basically says is that, what a frozen body basically tells Ansys is that, this surface is basically going to be just used for projecting and not for anything else. Right. So the question is, if we are working with an assembly, can we project the geometry onto from one part onto another? You definitely can. So you can. You'd still have to sketch it, I think. So one way that I would do it is I would make a plane that's kind of coincident with the feature that you want to project, and then kind of make a sketch that sketches out the kind of the outline of that feature that you want to project. And then once you have that sketch, you can basically follow the same steps as we followed just now. So I don't know if there's kind of an automatic tool for doing that, but you can definitely do it manually by drawing the sketch. Yeah. Mm-hmm. Yeah. So actually, if you want to kind of see this in action a bit faster, if you look at the bottom of the handout, you can kind of see the YouTube video that I based this off of. So this was definitely something that I didn't figure out myself. So this is something that I learned from YouTube. So if you want to see this, I think the video is only 2 minutes long, and you can kind of see it kind of in real time. Okay. So let's go ahead and extrude this. Okay. So let's go ahead and now that we have our sketch here, so let's go ahead and click extrude. So you can go and click extrude by going up here and click create, or you can click right here in this menu right here. Right. Okay. So now that we're in the extrude menu, we need to select the geometry that we want to extrude. So let's go ahead and click this guy, hit apply. Okay. So now we've selected sketch 2 as our geometry. So sketch 2 is the one that we just created just now. Okay. And so this part is really important right here. So then for the operation here, the typical way that you do extrudes is that you use it to add material to your model. So that's basically how I created the cylinder. Was I created a circle and I just extruded it. But we're going to change this here. So instead of adding material, what we're going to do is we're going to add frozen. Okay? And what that's going to do is it's going to create kind of a frozen solid that we can use for projection. Okay? You can change the depth here, but it doesn't really matter all that much. I'm going to change it just because it's a little bit obnoxious to kind of see a big kind of frozen structure. So instead of 100, I'm going to change this to 10. Okay. Okay. And then what you can do from there, you can hit generate. Okay. So you're going to see basically a blue solid appear here. So it's blue because it's frozen, like an ice cube. Okay. But you can just ignore that. But so the only thing that it did was it took basically our sketch and it froze it, so that Ansys knows that this sketch is not something we're going to use for geometry. It's just something that we're going to be using for projection. This basically kind of freezes it in place. Okay. So it's a little bit of a weird step to kind of create kind of an extra solid, even though we're not actually going to use it. But it's it's kind of a necessary step just to use this projection tool. Okay. All right. Are there any questions on that? Okay. So now that we've frozen the sketch, we can go ahead and project it. Okay. So let's go ahead and click Tools up here, and then go down to Projection. So this will create a new projection object, right? So we'll go ahead and left click that, and then we'll click this projection here. So then once we do that, we can see that we've changed kind of this details menu here. So we need to select two different things here. So first thing we need to do is we need to select the edges of the sketch that we want to project. Okay. So you can see right now we're on this edge selector mode right here. So let's go ahead and click all these edges. Okay. Okay. So you can hold Control and click, just to select all of them, and you're going to select all the edges of the sketch that you made. Okay. So let's go ahead and hit Apply. So you can see we've selected 4 edges. Okay. So that's good. And so the other thing we need to do is we need to select our target. So let's go ahead and click this. And then we can select the face that we want to project on. Okay. So we're basically, after we choose our edges, we can choose the face of the cylinder. Okay. So let's go ahead and hit Apply. Okay. And then once we're done with that, we've selected those things. We can go ahead and hit Generate. And it's a bit tough to see, but you can see underneath here, we basically inputted like we put a piece of tape on our model, which corresponds to the projection that we did. Okay? So this is a new surface that we can actually create, or we can apply boundary conditions on. So this is going to be really useful for us when we run simulations. Okay? So it's a little, I will say that it's a little bit different than how we did Ansys Activity 3, because in Ansys Activity 3, that extra surface was actually created as another whole body that was kind of bonded to our structure. Okay? So this is a little bit cleaner in that this is kind of a new kind of selectable surface, but it doesn't actually have any physical dimensions. So it basically just allows us to select certain parts without adding any thickness, right? Because I know when we did Ansys Activity 3, there were some people that had some issues with the with kind of that thin strip. Because if you remember from that activity, we had to specify a thickness of that strip, and depending on the thickness, it actually changed the results quite a bit. So that's obviously you don't want that. So you don't want your kind of your fake surface or your phantom surface here to affect your results, you know, in any way. So in this sense, this is a little bit cleaner because this just creates something that's selectable without actually, you know, introducing any new physics in the system. Okay, are there any questions on this before we kind of see it in action in Ansys Mechanical? Okay. So then after you've created your phantom surface or your fake surface, we're pretty much done in Design Modeler. So let's go ahead and close this guy. Okay. And then let's double click Model here to open up Ansys Mechanical. Okay. Loading, loading, loading. Okay, so you can see we've loaded into Ansys Mechanical. So you can see we have our original cylinder, and we also have our frozen surface here. So you know, obviously we don't want to model that, so we can suppress it. So basically, any frozen surface you can just suppress it. So you can right-click it and click suppress. Okay. So you can see that that solid's gone, but our projection is still here. Okay? So you can see now we can kind of select this little like band-aid area on our cylinder and apply boundary conditions on it instead of applying it on our entire surface. Okay? So let's give that a try. So let's let me just kind of give this just a simple mesh. So let me generate mesh. Okay. Oh, that looks kind of ugly. So let me reduce the size on this guy. Okay. So let me make this let's try 5 centimeters. Oh, that's pretty ugly. Let me make this 2.5 centimeters. Let's cut it in half. Okay, it's a little better. Let's go a bit lower. Let's try 1 centimeter. Okay, yeah, that's nice. Okay, and we're just under the limits here. So we have 25,000 nodes and 14,000 elements. So we're good to go. Okay. Okay, so now let's apply boundary conditions. So let's take an instance where we have kind of a cylindrical dowel here, and then let's say that we've taken this dowel and we've glued it to something else, and we've only glued it on this surface here. Okay, so let's insert a boundary condition here. So let's right-click Static Structural, and let's insert a fixed support, and then let's select kind of our projected surface here. Okay, and so what this will do is that this will fix the model on this surface right here. So, you know, say we glued this dowel to something else and it's going to be, you know, glued on here. And then now let's take this dowel and let's apply a force. So let's insert a force boundary condition. Let's use this surface right here. And let's say that we have a downward force. So let's define this in terms of components. Let me change the units. Oops. I don't want to solve. Let's change this so that we can do newtons. Okay. So let's apply a force in the x direction. So let's say that we apply a force of 10,000 newtons. Okay. And I didn't change the materials here, so it's made of structural steel. So basically what we have is a steel dowel. We've glued it on this kind of small surface here. and we're applying a tensile force here at the bottom. Okay? So let's go ahead and insert some solution fields. So let's do tellable deformation, and let's do equivalent von Mises stress, and then let's solve this guy and let's see what happens. All right. So let's look at total deformation. Okay. So you can see right here, you know, because we fixed it right here, we basically don't get any more deformation past this point. Okay. But you can see the deformation here is a lot just because we have this. Okay. And we can actually play the animation too. So you can see that, you know, the dowel is deforming a little bit, but it's staying fixed at that place where we fixed it, which is just on that small surface right there. Okay. We can look at the, oh, this is strain, sorry, I should have been stress, but stress and strain, they're more or less the same thing. And you can see that, you know, we kind of experience kind of the same things where we did before, where the stresses are kind of highest around where we fix it, because this is where kind of the displacement grade is going to be the highest, because we're going from a patch here where we've completely fixed it over to something else where, you know, the deformation might be pretty high, right? So this is kind of consistent where you would kind of expect the bending stresses to be relatively high right there. So that's basically it for adding phantom surfaces. So you know, this was a fairly basic example, but you know, hopefully you can use this and kind of twist it to be something you know, that'll be useful for your project, especially for, I think a lot of you guys have kind of interesting kind of areas of force application where you have a certain object or a person that's kind of standing on top of your object. So you can use this this tool to basically trace out the exact areas where that force is going to be applied, instead of kind of awkwardly applying it over the entire surface of your model. Okay. Okay. Any final questions on this? Okay. So if no questions on that, let's go ahead and move on to the next handout. So the next handout is on non-isotropic materials. Okay. So let me close this. Let me create a new project. I'm not going to save. It's okay. Okay. Savings for chumps. I'm just kidding. Okay. So I'm going to go ahead and create a new project. So we're going to make another static structural. Okay. And then this these lecture notes here are going to be on anisotropic materials. Okay? So before we jump into Ansys, let me pull up the actual handout just so we, you know, because there's a little bit of a forward section that I think would be useful to talk about. Okay. Okay. So here's the handout that I posted on Titanium. So this is a new handout. This is something I made this year. Okay? So this is basically going to allow you to input kind of more interesting material properties into Ansys. Okay? So, you know, for those of you who have, you know, taken like a strength and materials class, you know that kind of the field of material properties is very, very vast. So, you know, even though we're covering kind of basic anisotropic materials here, even then there's still a lot more than you can do. So like I've already spoken to some students who are interested in doing hyperelastic materials, which I don't think we're gonna which I don't think I have enough time to basically give it a good research and make a handout for it, but that's certainly available too. But then kind of besides that, there's other types of materials that you can do which are non-isotropic. Right? And what that basically means is that the material that you're going to be using is going to be stronger or weaker if you load it in different directions. Okay? So some examples of this could be like wood, or some of you are using, yeah, like wood, yep. Or some of you guys are doing 3D printed materials. So those are another type of material which are going to be anisotropic, which are going to have different strengths in different directions, right? So, you know, up to this point we've mostly just stuck with isotropic, just because isotropic is really easy. Because with isotropic materials, the only thing you have to specify is just the Young's modulus and the Poisson's ratio. So it's only 2 parameters, and they're usually fairly easy to look up. So, you know, that's what we've done. And for a lot of engineering materials, it's a pretty reasonable assumption. So for things like metals are often pretty isotropic. So, you know, you'll be defining that in terms of the Young's modulus. Sometimes you'll define in terms of the bulk modulus and the shear modulus, so that's kind of the same thing. And then you can just kind of be on your way, okay? But, you know, as we kind of mentioned, there's also a lot of engineering materials that are not isotropic, okay? So wood is one example of an orthotropic material, where the strength of the wood, or the strength that you basically experience, depends on how you load it, okay? So as everyone knows, wood comes from trees. So in a tree, basically you have these fibers that kind of run along the length of the tree. The original purpose of those fibers was to kind of transport water and nutrients to kind of all the different parts of the tree, okay? So it turns out wood, if you load it in the same direction as the grains, you know, that's going to give you the most strength, because the grains kind of form these kind of laminae within the wood, okay? But then if you try to load the wood across the grain, it's not nearly as strong in that direction. So then, you know, your wood's going to be much more likely to break, okay? So you can't really capture this kind of behavior with an isotropic material, because with an isotropic material, what that basically tells you that no matter which way you load it, you know, the strength is going to be the same. But we know that's not the case. So in order to properly simulate materials like wood, we need to kind of expand our repertoire and basically expand our toolbox to include kind of these orthotropic materials, okay? And some other kind of popular or other you know, orthotropic materials that you might see in engineering are 3D printed materials. So with 3D printing becoming a lot more you know, a lot more prevalent in the engineering world, right? Those are you know, that's something that's also going to be anisotropic, so that's something you need to take into account, and also composites, right? And also PETG. So I'm actually not aware of what that is, but if it's not isotropic, then that counts towards this lecture as well. Okay. So the nice thing is Ansys gives us the okay, 3D printed material. Nice, cool. And I learned my my new thing for today. Okay. So the good thing is that Ansys gives us the ability to model these non-isotropic materials. So it actually gives us a ton of flexibility, given that we can input the parameters for these non-isotropic materials, which is kind of a big if, but you know, it's there for us. Okay? So the majority of this lecture is going to take place within the engineering data module. Okay? So let's come back to Ansys. Okay, so I've created a new Ansys project here. And so let's kind of open up our engineering data. So let's double click this. Okay. And so we bring up our kind of our you know, this new menu of engineering materials. Okay. So you can see the only material that we have loaded right now is structural steel. Right. So structural steel is an isotropic material. So you can see you know, our material properties here are defined in terms of isotropic elasticity. So we have our Young's modulus and our Poisson's ratio. And then from the Young's modulus and Poisson's ratio, we've computed our bulk modulus and shear modulus. So that's all good. But what if we want to include a non-isotropic material? Okay. So one place that you can look is kind of the you know, the first place that you should look to see, you know, if you know, before you import and start inputting things manually, is see if there's something in the library for your material already. Okay. So remember, the way that we went to the library is we clicked this button right here called Engineering Data Sources. Okay. And then from here, we can actually look and see, you know, what materials are available to us. Okay. So we have all these different libraries. So kind of the first place that's good to look is general materials. So from here, you can see, you know, a lot of materials in here. Okay. So generally, a lot of the metal alloys will be here for you to use. And also we have polyethylene, which, you know, a lot of you guys use for the last Ansys activity for our plastic car. But actually, you know, a lot of the non-isotropic materials are missing from this list. Okay. So in order for us to account for them, we can either input them manually, which is what I'm going to show you today. Or what I'm starting to notice is that if you subscribe to some of these kind of material databases online, I've noticed that some of them offer a service where you can download a specific file, and then from that file, you can add that material property to your Ansys database. So I've never actually tried that, but I did see an Ansys button on there. So if you know any good kind of material databases online, that's something that you could look up and exploit for your project. I personally never used that, so you know, I definitely want to give it a try before I show you guys. But That's something that you guys can look into for your project if that's going to be useful. Okay. But anyway, so let's, for this activity, what I just want to do is just to kind of show you how to do it manually. Okay. So let's go ahead and add a new material here. So this is one that we're going to do from scratch. Okay. So the material that I'm going to add is the material that I've already kind of looked up the coefficients for, which I'm fairly certain are correct, but they might still not be. So I looked up the coefficients for basewood. So let's go ahead and create a new material called basewood. Okay. Let's go ahead and type it in and hit enter. Okay, so we can see we have our new basewood material here. Okay. And then from here, we need to start defining material properties. Okay. So what we've done in the past, when we've inputted our own material property, was we've used this isotropic elasticity. So in the past, we've double-clicked this in order to add it to our project. But in this case, we know that we don't have an isotropic material. And so in fact, we have an orthotropic material. Okay? So let's go ahead and click that. And you can see from an orthotropic material, we have all these material constants to define. Okay? Right, so the question is, it's not trivial to calculate the inputs for the orthotropic or anisotropic material. So it's always better to look them up. Yeah, that's definitely true. So, you know, with these kind of material constants, you know, it is really difficult to come up with these, especially with your own calculations. So if you can look up your material online, that'll tell you these constants, or you look up some kind of a research paper, which is what I did. So I have a paper that's referenced in the handout that you can look up for wood specifically. So if you can use data from there, then I would input it straight from the data sources and try to limit the amount of calculation that you do. Yeah. Okay. So you can see here for this orthotropic material, we have 9 constants that we need to determine. So we need to determine the Young's modulus, the x, y, and z direction. We have the Poisson's ratios in the xy plane, yz plane, xz plane. And then we have the shear moduli in the xy, yz, and xz planes. Okay? So we have 9 constants that we need to do. So 9 is a lot, for sure, but it can actually be worse. So, you know, notice how we chose orthotropic here. So orthotropic is a kind of a special kind of anisotropic material where we assume some symmetries in the material constants. But another material, so I'm just going to create one just so you guys can see. So if you want a perfectly, or, you know, if you make no assumptions based on the material properties and you make an anisotropic material by double clicking this, you can see that you actually have, I think, let's see, 1, 2, 3, 4, 5, 6, 21. Yes, 21 different constants that you need to determine. So, so this is really difficult. So I would say only use anisotropic material if you're absolutely certain about these constants. But you know, try to avoid it if you can. Okay. All right. So Scott has a question. So I'm reading some murmurings on the internet that you can import materials directly from Solidworks into Ansys if you assign the material properties to Solidworks and save it as an IGS. Oh, that's actually really nice. So I've never actually done that before. So that would actually be really nice. So if you can assign the materials in SolidWorks and that can save the material properties for you, that saves you a ton of work because then you don't have to go through any of this stuff. Then you can directly import it from SolidWorks. So that's so if you can do that, that would be really great. Yeah. Okay. But definitely, you know, verify that if you're going to do that. Right. But yeah, definitely verify that if you're going to use that SolidWorks feature, because I've never looked into it myself. I have SolidWorks on this computer, but it's my laptop kind of cries every time I open it, so I try to avoid it when I can. You know, definitely if you want to make use of that, verify that just to make sure that all the material properties are kind of importing properly. Okay. So back to this activity. So let's say that we're inputting the material properties for basewood, right? Oh, nice. So it looks like there is an extension built into SolidWorks that lets you import directly from SolidWorks into Workbench. So that's good to hear. Or export, yes. Yeah. So if you're familiar with that add-on from SolidWorks, I would definitely make use of that. Yeah. So that just goes to show, you know, SolidWorks is, you know, probably one of the best CAD softwares out there that you can use, just because it's really flexible and it has a lot of really great features to it. Okay. So for this activity, what I've said, or what I've defined is that, you know, since we're doing wood, I'm basically going to assume that the fibers run in the X direction. And so what that means is that the material properties that we assign is going to be strongest in the X direction. You know, I looked these up in the table that I've from the paper that I've posted. So I'm just going to input these directly. So I know that, let me change these to megapascal. So I know that the material properties are these just from the table that I've inputted. So definitely, you know, if you're importing this from Solidworks, you don't have to do this. But if you have some kind of weird material that you're using that's not in a database, oh yeah, it is expensive. Then you would have to do this manually. So just so remember, make sure you're in the right units. I'm just going to import these numbers. So I know this is 7200. This is 194.4. 475.2, 0.406, 0.346, 0.364, 331.2, 360, and 403.2. Okay. Okay. And so what I've done here is I basically inputted the 9 constant for this orthotropic material. Okay. And you can see, you know, after I've done that, all the yellow boxes were gone. Okay? So if you're kind of playing around with the engineering data here and you see some yellow boxes, those yellow boxes are kind of an indicator for you to say that you need to fill something in here before we can move on. Okay. So you know, before we started, all these boxes used to be yellow, but then after I put in the values here, they're now white. So we're good to go. Okay. So any questions on this before we kind of test this out? Okay. So let's go ahead and close out of here. So just to demonstrate this, I'm just going to create a simple cube for you guys, just to kind of show you. Okay. So let's go ahead and open up Design Modeler. Okay, so let's go ahead and create a cube. So let's change our units to millimeters. Okay. Let's create a rectangle. Let's go ahead and dimension this guy. And then according to the handout, I made this 100 by 100. Okay. So there's our square. Now we can go ahead and extrude this. So let's go ahead and hit extrude. Select the sketch, 100 millimeters. Okay. So this is just for demonstration purposes. So you know, I know a cube is obviously much simpler than you know, than any kind of your geometries, but I just want to kind of show you that there's going to be, you know, a different you're going to experience different stresses and different deformations depending on the direction that you loaded. Okay. So now that we're done with this cube, let's go ahead and exit Design Modeler, and let's double click Model right here. If I'm a little tired today, I apologize. So I had to make up 2 lectures from yesterday because right in the middle of one of my lectures, my internet dropped on me, so I couldn't finish those lectures. So I had to make them up today. So this is my 3rd lecture today. So this is probably the most lecturing that I've ever done in one day. So if I'm a little bit out of it, then I apologize. Okay, so we've brought in our cube into Ansys Mechanical. Okay. So let's go ahead and set our material properties. We're going to do this the same way we did before. So under geometry here, we're going to go ahead and click this solid. Okay. And right now our default here is on structural steel. Okay. So let's go ahead and change this to base wood, which is what we specified before. Okay. All right. And then let's load this sucker. So then let's first test a loading within the X direction. Oh, let's mesh first. That's going to be important. All right, so that looks good. We have hexahedrons because our domain is literally a big hexahedron, right? So let's go ahead. Let's try loading it in the X direction first. Okay. So to load in the X direction, let's go ahead and insert a fixed support. Let's put this in right here. Okay. And then let's go ahead and insert a force. Force, there you are. Okay. Let's go ahead and select this face, the opposite face. And then let's input a force of 500 kilonewtons. Okay. And let's view total deformation, and then stress, von Mises stress. Let's go ahead and hit solve. So from the total deformation here, you can see we even though we inputted a a pretty strong force, 500 kilonewtons, we only see a deformation of 0.732 millimeters. So pretty small. Okay. So let's see what happens if we try loading it. So remember that was a loading in the X direction. So that was in the direction of the fibers because we assumed the fibers were running in the X direction. So just like as we kind of predicted, when we load the structure within the same directions as the fibers, then we get relatively small deformation because the structure can resist loads in this direction quite a bit. So let's try loading it in a direction that's normal to the fibers. So let's go ahead and get rid of this guy. Get rid of this guy. Okay. So let's go ahead and insert a fixed support. Fixed support, and let's fix this guy right here. Question. Let's see. Right, yeah, and 3 different Poisson's ratios, yep. And then let's insert a force support up here. Right, and then we'll make this 500,000 again. Okay. So let's go ahead and click solve. Okay, so you can see the deformation was so large that Ansys gave us an error. So it said the deformation was so large compared to the bounding box that Ansys thinks that something's wrong. That's how bad it is. Okay. So you can see here our deformation is 24 millimeters. Okay. So obviously that's not realistic. So that's a strain of basically 0.25, so a 25% elongation. So the wood is obviously going to break way before it reaches this. But you can see here that when we try to load it in a direction that's not in the same as our fibers, we exhibit, much smaller or much lower strain. Okay. Right. And then finally, we can see what happens when we load it in the Z direction, just for completeness. So let's go ahead and get rid of this. Get rid of this. Okay. So let's insert a fixed support. And fix this guy. Right. Next, we'll insert a force. Select this guy. Make it 500,000. Okay, so let's go ahead and hit solve. Okay, and you can see here we get a very different deformation field too. So it's not quite as extreme as before, but you can see the deformation is distributed differently. Okay, and that's also a result of the orthotropic properties of the material. Where in this case, the Poisson's ratio is causing, this kind of very interesting, almost like parabolic deformation field in this structure. Okay. All right. So are there any questions here on anisotropic materials? Okay. So I would say the only thing I would be careful about if you are loading material properties from Solidworks, so I don't know if Solidworks does this, but you want to make sure that if you're doing something like wood, that the grains kind of run in the direction that you want it to run. So I would say just be careful about that, and just make sure that the strength is high in the direction that you want, because when you do orthotropic materials, the direction is really, really important. Okay, so if there's no more questions, that's all I got planned for today. So we ended quite early today, so there's still a lot of time for questions. So if you want to ask me questions on this or anything else, I'm open to that. Okay. All right, so the question is, how would Poisson's ratio dictate strain, or the grain direction dictate strain? So that's a great question that I am super not qualified to answer. So my knowledge of the way that wood grains affect the stiffness is limited to the paragraph that I read on Wikipedia when I prepared this this handout. So definitely, I would ask one of your professors who taught you strength materials. I think they would definitely be a much better source of knowledge for that. Yeah, but I wanted to prepare this handout just because I know some of you guys are working with wood. Some of you guys are working with 3D printed materials for your final project. So I just wanted to make sure that you guys are aware of kind of the tools that are within Ansys. But outside of that, I'm definitely not an expert at this stuff. So yeah, I would ask someone else about that. All right, question. So do most engineers who work with wood a lot usually depend on tabulated data? That's tricky. So I know with wood, I know a lot of it depends on kind of the moisture content within the wood too. So I know that there has been a lot of studies on how wood behaves and a lot of tabulated data, but a lot of it depends on things like the moisture content and like stuff like that. So I think they do. I think more or less they do depend on the tabulated data, but because I think wood depends on a lot of other factors, I think they try to make it so that their factor of safety is high enough such that even within variability of like moisture and stuff like that, then their structures are still going to be okay. That's my kind of gut feeling. But exactly how much they depend on it and what their methods are, that I'm not exactly sure. Right. So the question is, can the shell be applied here as well? Yeah, absolutely. So you can definitely apply shells and beams to these kinds of structures too. So the shells and beams will take that anisotropy into account. So the equations for that are going to be pretty complicated because you're taking kind of a 3D kind of understanding of a material property and you're kind of transforming that to a 2D surface. So it's, there's definitely some math that's going on underneath the hood, but I imagine Ansys can handle that pretty well. All right, question. So would 3D printed materials more likely be anisotropic than orthotropic? It seems like the latticing would dictate that because it's not normal to any one plane. Yeah, that's a great question. I would say that yeah, that's probably absolutely true. But I think probably there's some assumptions that you can make where you can probably assume that the 3D printed material you can probably model it as orthotropic, given that you have some assumptions there, because anisotropic materials, they're very difficult to use just because you have so many constants that you need to define. So if you kind of make some assumptions, you can probably model it as orthotropic, and I think it would be somewhat reasonable. It wouldn't be perfect, but I think it would be pretty reasonable. I think for most cases, I would say. Yeah. Right, so it seems like the subject is very focused doctorate level stuff, yet it seems many products are engineered with wood that undergoes temperature changes and different stresses in all directions. It seems weird that you need to have that level. Yeah, yeah, I hear you. I mean, it's, when you want to get into like the exact numbers of everything, definitely there's a lot to keep in mind. There's a lot to keep track of. So, so I think, I think one thing I'll say is that kind of my perspective from this is my perspective is I'm coming from the perspective of someone who did do a lot of research on this stuff, and who's used to kind of inputting kind of very precise parameters for everything just for the sake of modeling. So that's kind of what my background is in modeling stuff. So for the people that kind of work with these things kind of more on a more practical level, I think they're gonna have a much very different perspective on these things where I think they've kind of developed their own methods based on a lot of the same data, but I think they kind of use it in a different way that kind of works a lot more for them too, because it's even for me, just the thought of inputting 21 material constants for something that I want to model is a really high barrier for me to overcome too. So that kind of is a barrier for me to kind of do anything practical. So I think for people I think that do work with these things that design a lot of wooden structures, I'm sure that they have their own kind of methods to do this. Yeah. Yeah, so I think you're right. So I think a lot of it depends on kind of the standards that they use kind of in those fields that kind of incorporate a lot of the intuition, a lot of the data that they have here. Yeah, absolutely. Mm-hmm. So actually, my background is in fluid mechanics. So in fluid mechanics is actually a lot simpler to this because in fluids, there's we often just use the density and the viscosity. So I often only have to put two material constants. So solid mechanics it's a lot more complicated in that you really have to get the materials right, and there's a lot of different materials out there that you could use. Yeah. It's less complicated in terms of material, but it's more complicated in other ways. So it's they're both complicated. They're all really hard. Engineering is engineering. At the end of the day, it's all really hard stuff. It's just kind of different things are harder in some ways than other stuff. Yeah. Actually, speaking of fluids, I want to ask the class if there's any interest in this. Earlier this week, there was someone in the class who was interested in doing fluid mechanics for their final project. And I know initially I said there's no fluid mechanics just because it was hard to do. But actually, we sat down for an hour and we kind of figured out how to do fluid mechanics or CFD within Ansys. So I was wondering if there's enough interest in the class. Oh, you did that on your own. Okay. If there's enough interest in the class, I could make a handout for it. I probably wouldn't get to until it's probably sometime next week. But that's something I can do. And if there's time in the class, we can go over together on basically how to run kind of a basic CFD simulation within Ansys. So is there enough interest in the class for me to do that? Oh yeah, for your senior design project, yeah, you had to do that. Okay. All right. So yeah, sounds good. Okay. So let me do that. I'll probably do that sometime in the middle of next week. So I'll make a handout, and then we'll probably do kind of like a handout style activity. So nothing that you would turn in, but at least something that we could kind of work on together to kind of see how you would do. We'll do something basic, like maybe basic pipe flow. Yeah. So external flows, I don't know how to do, but I can definitely do internal flows. So we can do we'll do a flow in a pipe. Yeah. Oh, cool. Yeah, so Dr. Sanders did non-Newtonian versus Newtonian flows for blood. So that's actually good. So actually, that's a good segue too. So actually, Dr. Sanders and I, we've been talking recently to kind of, do something neat for, because we're doing virtual instruction. He actually teaches a class at the same time as me on Mondays and Wednesdays. So what we agreed to do is kind of like a seminar swap. So what I'm going to do is I'm going to talk about some of the research that I've done on fluid mechanics in his continuum mechanics class. So I think we're planning that for the last day of class. And then what he's going to do is, because he has more of a solid mechanics background, is that for our last day of class, which is Thursday, May 7th, he's going to give a talk on some of the research that he's done with finite element solid mechanics. So I'm actually really excited about that because I haven't actually seen like a full research presentation from him before. So you can actually really see, how a researcher like Dr. Sanders uses finite elements for his research. So definitely look forward to that. I think that'll be really, really cool. Yeah, so I mean, it's going to take place during our normal lecture time. So I gave him basically the Zoom link for our lecture Zoom meeting. So if you just come into lecture as you usually do, then you'll be able to see it. Yeah, so that'll be Thursday, May 7th. So I think 2 weeks from today. Yeah. Yeah. So if you want to see my presentation, I can send out the link. So it'll be from Monday. It'll be on Wednesday, May 6th, from 5:30 to 6:45. So I can definitely send out the link if people are interested in that too. Yeah. All right. Are there any more questions on this before we sign off for today? We still got a lot of time, so so if you have questions on your project, I think I might have gotten a few emails. Let me stop sharing. Okay. So does anyone have any issues with their project that I can answer right now? Oh, nice one. Okay, so you got it to work. A pivot error, yeah, a pivot error usually happens when the simulation is under constraint. So I think what you might have to do is you might want to add or make sure your fixed constraints or all the constraints that you put on your problem or do enough to basically fix it in space. So just kind of double check that. Another cause that I've seen for pivot errors is that if you are applying kind of a fixed constraint on a very kind of thin surface, basically on a surface that's basically only one element thick, that can cause some problems because it might not be enough to kind of fix the whole thing. So if that's the case, you might want to refine the mesh in that area where you're applying that fixed condition, just to make sure that it's doing that. So just to give you kind of an explanation, so a pivot error, what that basically means is that you know, after we apply the finite element method, basically what you're going to get is a large linear system. So a large left-hand side matrix and a vector, right? And so what Ansys is doing is trying to find basically a numerical solution to that matrix, and is doing that using a method, using numerical methods. So I think the one that they might use in Ansys is called Gaussian elimination. So with that, there's a lot of, they call it pivoting, where they kind of switch places in the matrix to kind of make it easier to solve. So if things aren't constrained well, then it has problems basically performing that pivot operation. So so that pivot doesn't mean anything physical. It's a numerical pivoting within the matrix, and that's usually because you haven't fixed it well enough. So I would kind of double check your constraints just to make sure that that those are okay. Okay. Let's see. Do you want to? Do you have it up right now? Do you want to show me on here? Let me stop recording.